So in this video, we're going to be discussing linear functions, identifying linear functions. What classifies as a linear function will be the first thing, or sorry, what classifies just as a regular function at the start of the video. Then we'll get into what classifies as a linear function. Then we'll be doing a little graphing and just a little more topics about linear functions. So the first thing that we're going to discuss is whether or not when we look at a graph, can it be classified as a function? So we're going to do what's called a vertical line test. So what you're going to do is try to imagine when we look at a graph, is there any vertical line that we can draw that goes through 2 points? So if you look at the first graph, you notice how, and we don't even need to draw lines in any particular order here, is there any line you can draw that goes through 2 points on that graph? And for this one right here, there is none. So basically this one is a function. So we can't find a line or a vertical line, kind of like an imaginary vertical line, that goes through that graph at 2 points. Likewise for this one, if I make vertical lines, there isn't really any vertical line on that graph that can go through 2 points, so that one also is a function. The next one's here, so these ones are actually non-examples of functions, so these are not functions. And you notice that for the first graph here, oh, well, this vertical line here goes through a point here, here, and here, so this one is not a function. And there's actually multiple lines where that happens. Likewise for this one, there's multiple lines that when I draw them through the graph, goes through more than 1 point. So this one also is not a function. So the name of the game is you don't want one x value to give you two y values. That doesn't constitute it as a function. Is it linear? Okay, so a subset of functions are linear functions. So out of all of the functions that are out there, there's a little group inside those functions that are just specifically linear. So linear functions are always functions. It's never going to be, yes, it's a linear function, but no, it's not a function. So if it is a function, we got to see if it is linear. And basically, to figure out if it's linear, you just have to make sure it makes a straight line. So it's really easy to see on these computer-generated graphs that it is a straight line. Notice that the first one here keeps a nice straight line all the way through. That one is a linear function. The next one also keeps a nice straight line, and that one is a linear function as well. So basically, it doesn't make a straight line. So some of the problems that you're going to see on your homework is it asks, is it a function? Okay, that's the number one thing you're going to answer. Is it a function? And if so, is it linear? So that's the second part you're going to answer. So if you look at the first graph here, the first question is it a function? So we got to go back to the vertical line test. Is there any line that I can draw that goes through more than one spot? And if you notice that this line right here actually goes through 3 spots on that graph. So this one is not a function. So if it's not even a function, it can't even be linear. So that's really all we can say on that one. You notice that if so if it is a function, we have to determine it's linear. The first one's not, so we don't have to worry about it. The next one here, let's see if it's a function. The vertical lines, is there any part on that graph that goes through 2 points? No, that one actually works out pretty well. So this one is a function. So, if so, is it linear? Well, does it make a straight line? No, it's kind of all wavy all over the place. It's not a straight line, but it's not linear. And there's your answer there. So these are more examples of identifying if they're functions, and if so, if they're linear, like we were just doing. So let's take a look at the one on the left. Let's see if it's a function. So the vertical line test, is there any point on that graph or any vertical line that goes through 2 points on the graph? That'd be a no, so this one is a function. And the next question is it linear? So does it make a straight line? Yep, that makes a straight line. So that one is linear. This one here, do our vertical line test. Is there a vertical line or more than one? There just needs to be at least one. Then we can see that there are plenty of lines that go through more than one point. Here, there, so on and so forth. So that one is not a function. So this next slide, we need to determine if the set of points represents a linear function. So you're going to be given some coordinates, and you almost have to imagine them on a graph, and basically, do they make a straight line? So you could do the way of just plotting the points on a graph, see if they make a straight line, but there is another way to do it that you don't even need to graph it. So we're going to do it that way. If you ever want to double check your answer and just graph those points on a graph paper and check to see if they make a line, go ahead and do that. But we're going to do it a different way. And what you do is, first off, look at the x values. 1 to 2 to 3 to 4 to 5. So notice how those all go up 1, or you add 1 each time for the x values. So those make a nice pattern all the way through. Let's take a look at the y values. We go from 2 to 3 to 4 to 5 to 6. So we go up 1, we go up 1, we go up 1, and up 1. And those all make a nice pattern. So each time we're going up 1 on the x value, we're going up 1 on the y value. So that makes a nice, kind of sort of a step pattern. And if the pattern is present in both the x and the y values, then it is a linear function. Next one here, we go from 5 to 4 to 3 to 2 to 1. So we're going down 1 on the x values. So it's okay if we go down. Then we go from 3 to 5 to 7 to 9 to 10. So we go up 2. We go up 2, but from 9 to 10 we go up 1. So if this was a positive 2, we would be linear, but since that is a positive 1, this is not linear, or not a linear function. Let's take a look at the last one. So we go from 2 to 1 to 0 to negative 1 to negative 2. So we go down 1, down 1, down 1, down 1. The x values are okay. And actually on the homework, I don't think the x values will actually have a different pattern, but make sure to double check. Looking at the y values, we go from 5 to 7 to 9 to 13 to 10. Okay, so we go up 2, we go up 2, we go up 4, and then we go down 3. So this one's kind of all over the place. So thus, this one is not a linear function. So we have to make sure those patterns are present all the way through the x values and the y values. So let's take a look at a few problems where we're going to graph some linear equations. So we have an equation here, and we're just basically going to graph that. So what we're going to do is make an XY table. We're going to graph these using tables. We'll later learn a shortcut on how to graph these. And pick some x values. I like to choose easy ones like 0, 1, and 2. You can use whatever you would like. And we just need to plug the x values in and get a y value out of it. So plugging in 0, I have y equals 2 times 0 plus 2. Make sure to multiply these together first. So 2 times 0 will give me 0. So y equals 0 plus 2. So y equals 2. Plugging in the x value of 1, we have y equals 2 times 1 plus 2. 2 times 1 will give me 2. So y equals 2 plus 2. Y equals 4 for that y value. So 1, 4. And plugging in 2, I'm going to do that work over on the left. Y equals 2 times 2 plus 2. 2 times 2 will give me 4. Y equals 4 plus 2. So y equals 6 for that one. So we have a point at 0, 2. We have a point at 1, 4. And a point at 2, 6. And since we're talking about linear functions or linear equations, should make a nice straight line. So if it doesn't, maybe go back to look at one of your points, maybe see if you goofed up somewhere, but it should make a straight line for all these equations. Next one here, I have y equals negative 2x minus 1. Let's make a little xy table. How about let's try negative 1, 0, and 1. Again, it doesn't matter which one to use. The ones that are closest to 0 are most of the time easier, so that's kind of why I use them. So let's plug those guys in. We have y equals negative 2 times negative 1 minus 1. Negative 2 times negative 1 will give me a positive 2. So positive 2 minus 1, so y equals 1. Plugging in 0, y equals negative 2 times 0 minus 1. Anything times 0 is 0, so 0 minus 1. So negative 1 there. And plugging in 1, I have y equals negative 2 times 1 minus 1. Negative 2 times 1 will give me a negative 2. Negative 2 minus 1 will give me a negative 3. So negative 1, 1. 0, negative 1. And 1, negative 3 for my points. And then make a straight line, so we know we're good. So to finish off the video, we're going to talk about some word problems. Now, word problems can be kind of scary, but these ones are really not too bad. So, transportation application. A train travels at a constant speed of 75 miles an hour. The function f of x equals 75x gives the distance that the train travels in x hours. Graph this function. So we just actually did graphing, so f of x equals 75x. You can think of that as kind of like a y equals 75x. The f of x is kind of treated like a y in these equation problems. So again, what we're going to do is pick a few x values, plug them in, get some y values, and graph this. And I have kind of a crude graph here, so I'm going to graph it on this. So let's choose x values of 0, 1, and 2. So if we plug 0 into the equation, we have y equals 75 times 0. So 75 times 0 will give me a y value of 0. Plugging in 1, I have y equals 75 times 1. So y equals 75. And an x value of 2, we have y equals 75 times 2, which gives me a y value of 150. So 150 for that one. So applying those points, I have one at 0, 0. I have one at 175. And one at 2, 150. So sometimes when you make these graphs, you'll try to make a straight line out of it. Sometimes your scaling is a little off. But there's my graph there. And the second part of the problem after we graph is we need to find the distance after 5 hours. So you can kind of think of a function as sort of like a machine. So if you wanted to find the distance after x hours, well, basically that's what x is. If you wanted to find out what it was after 1 hour, well, you just plug 1 in. Well, if you wanted to find out the distance after 2 hours, just plug 2 in. With 3, you plug 3 in. With 4, you plug 4 in. So finding the distance after 5 hours, all we have to do is plug in 5. So 75 times 5, that'll give me a 300, it should give me a 375. So you just take 75 times 5, and that'll give me a y value of 375. And we are in miles, so 375 miles after 5 hours. So one more word problem, just like the one we did. We have a movie rental store charges $6 membership fee plus 250. Sorry, not 250. $2.50 for each movie rented. The function f of x equals 2.50. X plus 6 gives the cost of renting x movies. So I didn't say it right here, but we actually want to graph the function. So like we did on the previous problem, let's make a little XY table. I'm going to use 0, 1, and 2 again, because you can't rent a -1 movie. You don't really want to go into the negatives. So plugging in 0, we have f of x, or y, equals 2.50 times 0 plus 6. Anything times 0 is 0. So f of x equals 0 plus 6, so f of x equals 6. F of x, plugging in the 1, we got 250 times 1 plus 6. So we have 250 plus 6, which will give me 850. So $8.50. Plugging in 2, we got f of x equals 250 times 2 plus 6. 250 times 2 will give me 5. So f of x equals 5 plus 6, which will give me an 11. So 2 movies will be $11 when you start up a membership fee. So 0, 6, 1, 850, and 2, 11. So something like that. And it doesn't matter if it's perfect. I'm actually kind of a little off on my dots here. I don't quite make a straight line, but that's okay. And we want to find how much it is to rent after 6 movies. So we just need to plug in 6 in for x in that equation. So 250 times 6 plus 6. That's what our function is. 250 times 6 will give me 15, and then 15 plus 6. So it should be $21 for 6 movies.